We're going to return to looking at limits today, and specifically when a limit has what we call an indeterminate form. If I have a limit of the form f of x over g of x, and if we have f and g both approaching 0, we call that an indeterminate form because knowing that the top and the bottom both go to 0 doesn't allow us to evaluate the limit. And some examples of that we've seen in the past. On this first limit, if you were to approach 1 in the numerator and denominator, you'd find that both the numerator and the denominator go to 0. So we have 0 over 0, which means that just by plugging in numbers close to 1, we aren't able to determine the limit. We have to do some other things, which we know in the case of this one, we can factor and then have x approach 1. Same situation on the second limit. As x approaches 0, sine of 0 approaches 0, and same on the bottom, we approach 0. So we again have an indeterminate form. It means that we can't determine the answer to this limit just by knowing that it's approaching 0 on the numerator and denominator. So we have to do some other things. And we have talked about a proof of this limit in the past. But there is another method that we can go to. And this is called L'Hopital's rule. And what I'm going to do below here is just give you a sense of, well, first of all, let you know what the rule is and why it is the way it is. It's not an official proof that I'm going to do. It's just to try to give you a sense of it. So we begin with the idea that both our numerator and our denominator must approach 0 for this strategy to be carried out. And the whole idea here is we're trying to do the limit as x approaches something of f of x over g of x. We got our 0 over 0, our indeterminate form. Alright, and the argument I'm going to give to you is that f and g can be approximated by the tangent line at that point through linear approximation. So the linear approximation for f of x, remember, was at x equals a is f of a plus f prime of a times x minus a. And for g, same thing with g. Alright, so we've already indicated that f of a and g of a were 0. So we can reduce this expression to this, which means that my x minus a cancels out. And so what I have here is that this statement is equivalent to this as I approach a. We're assuming that f and g are differentiable at this point. And we're coming up with this result, which says that the limit of f over g, where f over g is an indeterminate form 0 over 0, I will get the same answer if I take the derivative of the top and the derivative of the bottom. That's L'Hopital's rule. Alright, let's just apply this idea to those two limits above that we started with. In order to use L'Hopital's rule, we need to plug in numbers close to 1 and ensure that we have an indeterminate form. So we have 0 over 0 when we approach 1. So L'Hopital's rule simply says, if I take the derivative of the top and the bottom, and this isn't the quotient rule, by the way, it's simply the derivative of the top on its own over the derivative of the bottom, then this new limit is going to give us the answer to the original limit. And so as x goes towards 1, the limit goes towards 2. Okay, let's try it with sine x over x. Again, ensure we have an indeterminate form, 0 over 0, we do. So we simply need to do the derivative of the numerator, which is cos, over the derivative of the denominator, which is 1, make x approach 0, and we get an answer of 1. So I've tried to give you a sense as to why L'Hopital's rule is the way it is. And what you see here is the fine print on what the theorem actually says. The proof is quite technical and the details are quite technical, and the proof of this is beyond the scope of this course. Bottom line is, if you have an indeterminate form, 0 over 0, then this limit can be calculated by this limit. And that's true whether or not this goes to infinity, negative infinity, or an actual value. Okay. Furthermore, all of this can be applied to not only x going towards a, but x going towards any of these values, or to infinity. And it gets even better. Not only does L'Hopital's rule apply to an indeterminate form of 0 over 0, it also applies to an indeterminate form infinity over infinity. So if the numerator and the denominator both go to infinity, I can use L'Hopital's rule. Alright, so just one more example on that note. I have a limit to calculate here, so I can use my regular processes. If I let x go to infinity, I can see that the numerator is going to infinity, and so is the denominator. And so I have an indeterminate form. I'm therefore allowed to use L'Hopital's rule. You must remember to ensure you have one of these before you proceed with L'Hopital's rule. So if I do the derivative of the top, 3e to the 3x over 2x, and then try to evaluate my limit, I have the numerator going to infinity, and I have the denominator still going to infinity. So guess what? Yes, I can do it again. It's the great part about L'Hopital's rule. As long as the indeterminate form stays, I can keep going. So I'm going to have 9e to the 3x over 2. And as x goes to infinity, e to the infinity is infinity times 9 is infinity. Over a fixed number, that goes to infinity. And so that is my answer. On the topic of the indeterminate form infinity over infinity, if you have a negative in front of either one of the infinities, that's still considered to be an indeterminate form.